Hello, today we are going to understand how security enforcement works in Android, especially in SELinux, and how OEMs maintain and extend this security model. Android security is not just about the permissions. So when you develop any app, you give the permissions. It is not about the security of those only about those permissions. It is enforced at multiple layers from kernel to framework to system services. The most important enforcement mechanism is at kernel level. Okay, there should be a enforcement mechanism at the kernel level, and that enforcement level is known as SELinux. So why security enforcement is required? Before Android 4.3, Android mainly relied on Linux user IDs or UIDs isolation, file permissions, app sandboxing, and these things were not enough. There was need of a mechanism above this UIDs, file permissions, and sandboxing. So if a system service was compromised, it could access hardware directly, modify system files, it could change your privileges, and that could lead to the issues. So Android needed a mandatory access control system. This is where SELinux comes in. So what is SELinux? SELinux is security enhanced Linux. It is a kernel level. It is a kernel level mandatory access control system. So whenever we talk about the SELinux, this is a kernel level security mechanism. For so we use the SELinux for security, and this is when we talk about security, this is kernel level security, and it is a type of uh, mandatory access control. So there is a DAC, and SELinux falls in the category of MAC, that is mandatory access control. So we have seen it is a kernel level security system. So unlike Linux permissions, the DAC, where the owner decides the access, SELinux writes like system-wide security policies that decides the access. So there are some libraries and there are some policies that are not that are defined by the system, that are defined for the system wide for the security purposes, and that will decide your access. So how the SELinux works? System wide security policy decides your access. Even if a process runs as root, SELinux can still block it. So unlike the tag, if even if a process is root process, you can block it by using the uh, SELinux policies. So this is known as least privilege enforcement. Okay, so Android 4.4, it is by default shipped in enforced mode. After Android 4.4, Android ships SELinux in the enforced mode. So previously it was in permissive mode. Before 4.4, that is 4.3, it was in permissive mode. From further on, from 4.4 and further versions, we ship SELinux in enforced mode. So permissive mode means violations are logged, it doesn't block. Enforced modes mean violations are logged, and it is also blocked. You cannot further perform any action after those are blocked over there for that particular file or particular process for which it is blocked. So this is a major security milestone from 4.4, Android 4.4. Every access is checked against SELinux policy. So how security is gained and maintained? Let's understand how enforcement actually happens. When a process tries to access a file, open a device node, talk to other service, or access binder or use hardware, the kernel checks whether the process um, SE, what is the process SELinux domain. For the first, the kernel will check what is the security Linux domain for this process. What are the object labels? What are the policies that are allowed? So what the kernel will check? Kernel checks for what is the SELinux domain. SELinux domain for the process. Then what are the objects that are labeled? Objects labels. And third, it will see what are the policy that is allowed. What the policy allows. If the policy says allow, we will grant the access. If it says allow, we will grant access. If the policies say don't allow, the access is blocked. We will be that process will be blocked further on from there. So even root cannot bypass this file. So if you say some malicious uh, process is part of your Android system and it tries to deny the policies, even if it is a root, it has a root privilege, it will be blocked over there. So security is gained by strict domain isolation, limited access rules, explicit allow rules. Nothing is allowed by default. You have to define the explicit rules, allow access, and you have to register the domain. So policies are written in .te files, that is type enforcement files. So these are the files which has the policies and they are compiled into SE policy. There are platform policies, platform SE policies that are from AOSP. Platform SE policies, those are from AOSP. There are vendor specific policies, these are from OEM. OEM is nothing but original equipment manufacturers. So they define some policies, those are vendor policies, and there are some device specific policies. So libraries, we I have already told, it is a set of libraries and policies. These are the type of policies: platform policies, vendor policies, and device specific policies. Then what are the libraries include? We will be using a library that is lib SELinux and lib SE policies. Okay. At runtime, kernel enforces policy using these compiled rules. So we will further on see it in more details.